Hi, everyone. We're continuing with lesson 25, and we're going to explain why these interval estimates for population parameters, such as a population mean mu, are going to be called confidence intervals, or CIs. That will be my acronym for confidence interval. Now remember, let's say that our TA, Igor, tells us that he believes that the population mean test score for the 1,000 students is somewhere between 70 points and 78 points. That's an interval estimate. Before, I might have labeled this axis with mu. I'm labeling it with points because that's the unit. I'm not going to label the axis with mu anymore because mu is a value that we're targeting. Here, I just wanted to remind you that these were possible values for mu. Okay. But Igor says our confidence interval for mu is between 70 points and 78 points. It's the interval consisting of these values. And then I might ask Igor, how confident are you? How sure are you? Back in the game show, Who Wants to Be a Millionaire? That was a famous question that was asked. How sure are you? When you asked your phone a friend how confident he or she was that an option really was an answer. How sure is Igor that this contains the true population mean, the thing we're trying to estimate? So that confidence level, how sure are you, is a probability that is often expressed as a percent. And when we attach a confidence interval to an interval estimate, we have a confidence interval estimate for that parameter. Okay, and of course the idea is that the interval estimate should be likely to contain the value of the parameter. In fact, the most common confidence level is 95%. It should be a high probability, like 95%. There's no point in having a 10% confidence interval. Okay, so the confidence level is the probability that the confidence interval contains the true value of the parameter. The most commonly used confidence level, again, is 95%, and this is the typically assumed confidence level in published studies and news reports. In fact, many statisticians are irritated by the fact that when polls and other studies are reported by the news media might report the margin of error, like in a poll, for example, but the news media almost never tells the audience, hey, the confidence level is 95%. But that is typically the assumed confidence level. You should know that as a news viewer. Granted, the news is not very pleasant to watch today. All right. So some examples of confidence levels and related confidence intervals. Let mu be the population mean IQ score of American adults. IQ is meant to measure intelligence. Bear in mind, I'm not saying that I have much confidence in this kind of measurement, but these are common examples used in statistics books. Let's say a psychology professor wants to estimate mu, the population mean IQ score of American adults. So the professor analyzes a sample of American adult IQs, a random sample. Let's say that the sample mean for the sample, x bar, is 101 points. And the professor also finds the sample standard deviation or variance. You do need a measure of spread, as it turns out. So based on this sample data, well, I should say sample statistics. Based on these sample statistics, which are based on the sample data, the professor can construct a 95% confidence interval for mu, the population mean IQ score for all American adults. And let's say that this professor, maybe with the help of software, Excel or StatCrunch, let's say that the professor finds that the 95% confidence interval, using the professor's methods, will go between 98 points and 104 points. These are the limits of the 95% confidence interval. The interval consists of these values and all values in between. Technically, I'm using a bracket interpretation of this interval, but don't freak out about it. It doesn't matter if you put brackets or parentheses in this class. Okay, technically, if you include endpoints, you should put brackets. All right, let's now interpret this confidence interval, this CI. So here's the interpretation. We are 95% confident that this interval contains the population mean IQ score of American adults. So we're 95% confident that this interval contains mu. But of course, when stating this interpretation using proper English to a layperson, you want to avoid the Greek letters. You want to write out what mu is. Mu is the population mean IQ score of American adults. So you should write that out. If you're rushing on a test, you could at the very least do something like a star here and point to that at the very least. But you should write out what mu represents. You're writing out an interpretation for a layperson who doesn't really know statistics. Okay, so that's basically the typical American adult. Now, some books, such as Mario Triola's book, object to saying that there is a 95% chance that mu falls in the confidence interval. So there's some semantic objection to this term falls in. I don't have such a strong objection, but here's Triola's argument. Triola's argument is kind of a Zen argument. Triola is basically saying that mu, the population mean, is a fixed but unknown target. So there is a population mean IQ score for American adults. Granted, it might depend on the type of test or whatever, but let's say that mu is a particular fixed but unknown target. There is a population mean IQ score for American adults. We just don't know what it is. We might not ever know what it is at any given moment. But let's say that mu is a fixed but unknown target. Then mu isn't really falling anywhere. So if you consider the variety of confidence intervals that you might construct, let's say that you have different psychology professors who take different samples. Maybe you get this confidence interval from 98 points to 104 points. Notice that the sample mean lies in the middle, 101 points. In fact, that was stated in the previous example. This was the confidence interval, and the sample mean, of course, is right in the middle because we have symmetry about the sample mean for the confidence interval for mu. So this was our psychology professor's interval. But maybe a colleague across the country uses a different sample and gets this confidence interval, maybe going from, I don't know, 95 points to 100.5 points. Maybe another colleague gets this confidence interval. And maybe another colleague gets this confidence interval. Now let's say hypothetically, mu turns out to be 100 points. Theoretically, a number of IQ tests are structured so that 100 points is meant to be the mean IQ score. But that's rather hard to calibrate, though. But let's say that, in fact, the true value for the population mean is 100 points. Well, then, your colleague over here, the one who gets the confidence interval between 101 points and 105 points, that one misses the mark. It turns out this one misses mu. It doesn't mean that your colleague is an idiot or doesn't know statistics. Maybe it was just a matter of extreme sampling error. I mean, we're allowing for some sampling error, but maybe this colleague was just unlucky. This colleague just happened to miss the mark. So mu is a fixed but unknown target. It's not really falling anywhere. The question is, does a confidence interval contain the actual value of mu or not? And again, perhaps we may never know what the true value of mu is. At least in an election, we know what the result of an election is. We think, if the votes have been tabulated accurately. That's a big if. And by the way, what's a way that we can interpret the confidence level? I was saying here that the professor was constructing a 95% confidence interval for mu, the population mean IQ score of American adults. Well, what's one interpretation for 95%? Well, one is that when the confidence interval is constructed, then in principle, there is a 95% chance, we are 95% confident that this confidence interval will in fact contain the true value for mu. If mu is in fact 100 points, then this confidence interval up here is good. It works in the sense that it does contain the true value of mu, 100 points. Whereas this confidence interval, although it might have been intelligently constructed, it may have just missed the mark. Maybe it was just a bad sample for some reason. And maybe not because of bad design. It was just a bad sample. The professor was unlucky. Well, one interpretation for a 95% confidence interval is that if you imagine many confidence intervals being constructed, let's say 100 of them, and they're all 95% confidence intervals, and let's assume they're all constructed appropriately. That's a big assumption, though. But let's assume that you construct 100 confidence intervals constructed appropriately, based on 100 varied samples. So you might have 100 colleagues across the country who took 100 random samples. They could have even had overlapping people in them. And these 100 confidence intervals are constructed. If these are all appropriately constructed 95% confidence intervals, then about 95% of these, or about 95 or 100 out of 100, should contain the true population mean, 100 points, and about 5% will not. So here's a freaky thing about statistics. If the methods are applied appropriately, statistics predicts its own failure rate. So there's a certain humility here. Statistics admits that you might get a bad interval sometimes. So there's a humility there. But there's an arrogance in that it predicts its own failure rate. It predicts that about 95% of these confidence intervals will contain the true value of mu, and about 5% won't. So there is some arrogance there. All right. Now, if you don't believe me, let's take a look at this applet. It's the Rossman Chance applet from a couple of professors at Cal Poly San Luis Obispo. In fact, let's take a look at this applet in the next video.